All right, thank you. It's a pleasure to have the opportunity to speak here, and I'd like to thank Mariana for the invitation. And when I think about what to talk about with the opportunity, and I look at the agenda, and one is that we're supposed to talk about the measurement of gravity, and two, this is probably going to be the last, or one of the last talks about the clocks and atom parameters. I thought I'd provide some perspective of sort of more unified view of clock and atom parameters in the context of discussing of drag-free measurement, because when you talk about the gravity measurement, you inevitably have to talk about the drag-free, means there's only gravity working on it. And so if I do have time, then I talk about a NAG. That's a NAG mission concept study we've been working for a number of years that going to put a tetrahedral configuration of clocks and atom parameters in the solar system, and motivated by dark energy detection, but also can be used as a multi-science facility for from gravitational wave detection in the middle band to dark matter to even looking possibly for unknown like planet 9. And so it's very much ongoing progress, and hopefully we'll have some propagation come out very soon. But in some sense, that'll be probably one version of PFAS, so to speak, I hope. And so if I have time, I'll try to talk a little bit. Anyway, so I'll start this chart. You've seen them many times. And so the clock precision accuracy has really steadily improved to a fantastic level, and the 10 to the minus 18th, 19 now pushing to 10 to the minus 20, 21. And often the question is that what is good about it? And the motivation usually come up with is that, well, gravitational strain is on the order of 10 to the minus 19 and below. So if I have a clock that is good, then I can measure gravitational wave with clocks. Indeed, there are many proposals, or several proposals out there to do that. And so I want to step back a little bit. So what exactly clock is good for in terms of gravity measurement? Again, from my perspective. And so you have a sort of space-time gravity field here. Often the clock used for gravity test is time dilation predicted by general relativity. And so the clock missions are usually to have large differential gravity potentials and try to look at the difference between the clock and in terms of dilation measurement. Of course, you heard also you could also looking for unknown interactions in the form of change of fundamental constant. Therefore, the clock rate. And so most of gravity measurement, however, is not for time dilation or clock ticking rate change, but rather have test bands and use a laser ranging to look at the Doppler or the distance change. And for that, you need a ruler, and really the clock is provide a ruler for such a measurement. And so this can be used for gravity force measurement and gravitational wave, and also unknown forces of gravity nature, like dark energy, Fick's force, or violation of gravity. And I should say that 2 points to make. One is that in terms of gravity force measurement, direct test mass is always going to be larger effect than time dilation. That's why you're not using time dilation for gravitational wave detection. And I had some conversation with, even though with people, and even though it's proposed that one can use redshift for geodesy in terms of leveling, and that's a great idea. But in terms of actually mapping the Earth's gravity field, for example, using test mass is far more sensitive of precision, higher performance than redshift measurement. And the other thing is that we use clock term pretty generously, and the clock is to a horologist. Clock is really the only purpose for clock is keeping time and for synchronization, and for the rest of all the measurement is really as a frequency standard, not a clock. And the difference that if you actually add a counter to your oscillator, then you can count how many cycles and therefore accumulate the time. And therefore, for example, atomic clock on the JPL satellite, their formal name is like Lubedian clock, is actually Lubedian frequency reference standard rather than clocks. And I just kind of point out that. For gravity measurement, there are two sort of prerequisites. One is that you need a precision laser ranging to do the distance measurement, and two is a drag-free test mass. And so now we actually LIGO already detect the gravitational wave, and LISA is on the way, and we don't have clocks at the 10⁻⁹, or at least we don't have lasers at 10⁻⁹ or betas, but yet we will be able to do that. So why? And the trick is that this is a sort of technique already discussed in this meeting conferences in several contexts, looking at the correlation and suppress the common mode. And in the LISA case, you have two arms. Well, actually, LIGO will be a better example. LIGO, you have two arms with exactly equal. So and you have the two arm interferometer, and you have common laser gets mixed, and so you cancel entirely all the laser noise. LIGO never have to worry about in some first order degree of laser frequency noise. And for LISA, however, because large separation of million kilometers, and they never can really, in orbit dynamics, they never can really make the two arms are exactly equal, so they are always about 10% of distance variations. And in order to actually cancel out the common laser noise, they use so-called time-delayed interferometer, in the sense that they actually measure the return phase with a local oscillator, then do the time shift to cancel out the laser phase noise, but can preserve the gravitational wave signal, and so this is the basis of laser ranging technique that without using high performance laser or clock to 10⁻⁹. In fact, LISA laser frequency requirement is on the order of 1 part in the 14th, while strain measurement can reach 10⁻21 and below. And the other key requirement for gravitational wave detection, or LISA in that case, is drag-free. Now, the drag-free drag term, it means really just the non-gravitational force. And for satellite, it usually means sort of atmospheric drag, which is easy understood, and this is where a term comes from, but it can be any other non-gravitational force, like solar radiation. But in reality, if you just build a box, all those things will go away. But there's a very persistent local disturbance that the spacecraft self-gradient, which is much more a serious problem. This is a little bit similar to the ground gravity gradient noise that I talked about. It's really the local gravity noise, and it's the relative motion between the test mass and the spacecraft. And if your spacecraft relative test mass changes on the order of nanometer, you will have sufficient gravity force due to the spacecraft itself, even though you try very hard to make your spacecraft sort of mass symmetric and put the test mass in the middle of the spacecraft. So the requirement over there, overall, in order to achieve the 1/15 meters per second squared root hertz, you would have to have sort of a control of separation between the test mass and spacecraft to 10 nanometer per Lud Hertz. That's a very stringent requirement for that matter. I just want sort of like appreciate how significant this problem is in terms of flying drag-free, in terms of gravitational wave detection of LIGO. Of course, tremendous effort getting double pendulums, everything to get it sort of drag-free in one direction, I suppose. Anyway, so now I'm going to talk about the clock. So now you have a better clock, and let's say you have 10 to the minus 19 clock. What you can do in terms of doing gravity measurement? Well, you were doing exactly the same thing. So now because you have a local clock now here, you can compare with your lasers. You can do exactly what Lisa is doing and sort of doing time delayed interferometer, in the sense that interferometer is really the laser interfere with sort of atomic oscillator itself. So we would call it sort of a quantum atomic phase meter, and the interaction will register the phase here and the phase here. If you do the time delay to cancel out the common laser phase noise, then you will be able to get the gravitational signal. And so this allows you to really do a single arm interferometer rather than two arm interferometer. So in reality, everything else aside, it seems that if you have a 10 to the minus 19 or better clock, all that allows you to do is do a single arm interferometer. And if you, especially gravitational wave, is sort of a quadrupole field, then you may actually get some gain for two arms. And of course, space flight is expensive, so you can make two satellites rather than one, three satellites will be sort of cheaper. But anyway, so we did look at this in the context of this, and about 10 years ago, and so we did the sort of same way as Lisa time delayed interferometer using atoms as local clocks to compare the phase between the laser in a common laser system. Indeed, we will get recover the gravitational signal here, the string here with other noise, but all the laser noise goes away. So this is sort of we call it a single-legged bandit. You can use a single arm to do the gravitational wave detection. So this is of course really not in some sense to me it's not something new. What was discovered as a result of this is how we're going to do the using clock for gravitational wave measurement, and so how we're going to make clock drag free, and that was the question. And so this actually a question really separate whether you actually use the atoms as a clock versus the atom used as an atom interferometer, and I'll try to illustrate that. So in early talk, Shimon a couple of days ago already talked about using clock as a way to do the gravitational wave detection, and in order to make the clock drag free, what you can do is you can tie your atoms in this lattice to a test mass, and the test proof mass can be exactly the same as Lisa proof mass, and the atoms just tied to it. Since atoms have very little mass, so it doesn't matter where the atoms are going to be, and there was little force to be on the test mass, so there's no drag, and everything will be cool. And you can do that, and you can do exactly the one-legged bandit skiing with just one arm. And the advantage of that is, of course, the atoms are tied to the big mass, so there's no photon recoil to speak of. You don't have to worry about that. And there's no atom velocity spread because, again, it's trapped in a lattice. And because all the atoms in a small volume, you can control the systematics much better than otherwise. And this explains why today the optic clock gets 10 to the 19 stability now. Atom interferometer, if you calculate equivalent coherence time and everything else, is pretty far from the 1 part 10 to the 19th precision that you would achieve. And so there's some way to go. And of course, the difference is that for this, you need to fly the satellite drag-free, which is a very expensive endeavor. Even with LISA Pathfinder, they only demonstrated within factor 10 of what LISA would need for drag-free reduction. On the other hand, you can just let atoms free fall and without attached to anything. And and you treat it as a clock. So you say, oh, if you do the clock, for those who actually run the clock, you can just do a Ramsey two separate pulse interferometer, and that will give you a clock. Of course, the free fall atoms has a velocity and have velocity spread. So that's a very terrible way to run a clock. So in order to do that, and as you know, for those who do the NMR, this is just nothing but a sort of inhomogeneous distribution. And if you actually add pi pulse or reverse the phase to pi, then everything will have a spin echo and collapse. And this is exactly what well, in a simple term, what the middle pi pulse is for is you apply a middle pi pulse, you can sort of reverse the direction of spin precession, and then the velocity terms disappears. And so in some sense, now you have a pi over 2, pi over 2, and this is exactly typical light pulse interferometer, and which is independent of velocity of the atoms. And this is where actually originally we sort of come up with optical transition using based atom interferometer for gravitational wave detection. And so if you complete that, then you get the phase record a little more complicated than the clock phase, but nevertheless you have laser phases. But at the same time, because the momentum exchange between the atoms and the photons, now you also have extra term, which is this, or you see in the many times in atom interferometer, this is KIT squared. And so this is A will be the acceleration of the atoms. And if you have a drag-free system, then this acceleration goes away. You just have a pure phase meter. But on the other hand, if you don't have a drag-free system, then you actually give you a tool to measure the acceleration, say, with relative to a drag-free atom interferometer. I'll talk a little bit later on that. And so what's the difference? So the good thing is now if we have totally drag-free atoms, then we don't have to fly spacecraft drag-free. And so that will be a big saving. The price to pay is that now you have to deal with photon recoil. We know how to deal with that. We just run atom interferometer mode. We have to deal with thermal velocity. Again, we know how to deal with that, except on the transverse modes, the cloud actually expand, which is a big problem for atom interferometer, especially you want to have a longer interrogation time. Of course, if you actually really have larger momentum transfer, that means you have a larger split of atom wave packet, so the spacing between two different arms are much larger, so you need a much bigger space for run the interferometer. And larger space, of course, is harder to control everything, all the systematics. So this is sort of what the difference in terms of using intrinsic atomic oscillation, whether it's as a clock or as an atom interferometer, is based on whether you want to choose the atom to be drag-free or tied to some bulk test mass. All right, so now let's look back about this is a LISA sort of schematics of a drag reduction system. You have test mass, you have a cage, and so there's servos, microthrusters to have a spacecraft follow a test mass. And now, as an atom interferometer, as we know that we can actually measure the acceleration or actually the distance change, so we can simply replace that with atom formula inside the cage rather than a proof test mass. And the point is that then the atoms can be reproduced and always in the same place all the time. Then potentially you don't have to keep the satellite follow the test mass. Therefore, you don't have to fly drag-free in some sense. And in fact, drag-free requires a lot of fuel. That's the typical limitation of lifetime of such a mission is the fuel consumption for drag-free flying. And if you actually have two test mass and run each side, then if you just work out the atom in the formula, basically measure the motion between, let's say, this reference mirror to the free fall atoms, and this also on this side, and between the two mirrors, you use a standard laser ranging, and then you actually can get exactly as a large gradiometer or differential measure between the two drag-free satellite. And the only thing, as I mentioned, is that in order to have a high performance, a longer interrogation time, then the wave packet is spread quite big, and not only that this cage need to be very large, on order of like a meter or longer. Actually, the wave packet separation, I mean, you already see Casavich's tau, the packet are already separate, two packets are already separate meter, order of meters, and so that's not quite a good thing to implement. Yeah, and also remember the LISA requirement, you need 1 part 10 to 15 meter per second squared hertz of self-gradient force reduction, and with large atomic cloud samples, sampling entire sort of interior of a spacecraft, it's very hard to get that kind of control, and especially when you have things, thermal changes and so on. And so the way to get around that, I think it was first appeared in sort of Jason Hogan's paper, is that, well, since we are in space and in deep space vacuum is very good, so we actually can just push the atoms all into the space vacuum and far away from the spacecraft. And if you do some calculation, then you find that if actually I can push the atoms to 5 meters out to side the spacecraft, then it's far enough. The spacecraft self gradient is small enough that we only need 10 microns of jitter control, and 10 micron is actually the drag of spacecraft in the deep space is less than 10 micron of acceleration. So that means that we can indeed, if we run the atom formula outside the spacecraft, then we don't have to worry about the flying spacecraft drag-free in that sense. All right, so that's enough for how much time? I still 20 minutes. Anyway, so
you have about 5 minutes.
Oh, 5 minutes, nothing. Okay, and so I guess the takeaway point is that the atomic intrinsic, or if you call it quantization of energy levels of atoms is quantum in nature. Clock stability provides a possibility of a single arm interferometer measurement without relying on equally stable laser and without relying on two-arm interferometer to cancel the common laser phase noise. And so trapped atom clocks requires flying drag-free, but for gravity measurement, but otherwise the technology seems to be much more mature now. And if we want to, well, I guess science maturity, that the fact that the clock already get to the 10⁻⁹ demonstrated is much more mature in terms of the precision that can be achieved, while totally free atomic clock working in the form of atom formula And it does allow you to have the possibility of flying the measurement without drag-free satellite, which potentially is a lot of saving over there. But I think there's a lot that need to be worked out for that to work as good as the clocks today, I guess. But separately, atomrometer, I mean, this is already mentioned several times in different contexts. Atomrometer can be used as accelerometer that can simply do the local measurement. So if you make the atoms drag-free locally and measure the rate of motion between the spacecraft, then you can use it as a local drag reduction system without flying again, flying drag-free. And so I don't have time to go through the NIAC concept. What I'd like to just very quickly say is that this is already discussed. The dark energy is a vast part of the universe that we know nothing about, and there's quite a bit mission just looking at what the dark energy is. But all those missions just merely to tell you the history and the behavior that you can observe, but never really tell you what the nature of dark energy is, whether it's just Einstein cosmology constant, or it's a new field, or it's a modified gravity. It's difficult to answer that question. And but if it is a new field, then we're likely to interact with no matter, and that will give us a tool or window into the dark energy. And so if we find a way to probe that, and then we have a chance to understand exactly what the nature of dark energy is. And I'm not going to go through this. We did a little bit of simulation. So there was a little bit dark energy discussion earlier in optomechanics systems in terms of the different models of dark energy, the thin shield models, chameleon and symmetron, which is more for thin shield model. And there's a Galilean field, which is much more, I would say, astrophysics, better motivated model. But this is a much larger screening radius and much harder to detect, and because the screening radius is many pixels, and so whatever the effect in the solar system is very small. And how small it is, we did some simulation, and this is a highly nonlinear equation, by the way. We collaborate with Caltech fluid dynamic people. Actually, they know how to handle the nonlinear differential equations. And then we find that the possible Galilean field is the order of 10 times smaller, 10 orders of magnitude smaller than gravity force itself. And so we propose to kind of have a tetrahedral configuration of 4 spacecraft drag-free. By now you know what drag-free means, and there are different ways to do it, and have laser ranging to the precision very close to, actually better than the laser ranging, and so we can fly this thing in the solar system in the elliptic orbit, just to be able to vary the distance from the sun, because basically to look at a violation of inverse square law, because the Galilean force is actually 1 over root r rather than 1 over square. So there's a little signal we potentially can see, and yeah. So with this configuration, it turns out I'm going to skip this. Okay. So with this configuration, the designed separation of satellites is on the order of 10 kilometers to 100 kilometers, so far shorter than LISA. But turns out that if you calculate, everybody's talking about gravitational midband. It turns out this is a very good system for detection of gravity midband as well. We did some sort of back of the envelope calculation how good it can be, and this is where Lisa is in the low frequency domain, this is likely in the high frequency domain. And nice thing about have this auto plane configuration is that you actually have the ability to do some cross correlation measurement that can give you a chance to look into possible stochastic background, not just excess power that Lisa is trying to get, and there are conjectures or beliefs that in the initial Big Bang that there could be very early stochastic gravitational wave signals. But on the other hand, they may be overwhelmed by a much stronger so-called foreground signal, so that remains to be seen. But again, the non-planar structure can also give you a sort of instant polarization of gravitational wave measurement rather than relying on the orbiting itself. So in the end, just to conclude, and we haven't given a really good definition, but I have a reference. This is sort of a phase 1 report. It's on a NASA website. We have not published the peer-reviewed paper, but it's coming out. And so I would just say, in the end, this mission will be able to probe dark sectors, both dark energy and dark matter, and also, of course, can certainly just simply one of R square inverse law violation experiment, sort of a little more model agnostic test, and we can do gravitational wave detection in the midband. We can also, there are some studies of using the same facility for nature of quantum gravity as discussed before, especially in some of the in the non-Gaussianity of atomic systems, because we have huge atomic systems used in the mission. And in the end, we can also just use for precisely map the gravity field in the solar system, and perhaps have a chance to actually see on some unknown planets like a planet 9 that people always suspect was existing there. So I'm going to stop here, and thank you.
Okay, questions?
Yeah, thank you very much. I'm curious about this free fall clocks, and I have a question with the work with Shimon. One of the things that we showed with this lattice clocks for gravitational wave detection, one of the things you can do is you can apply also dynamical decoupling in order to tune your sensitivity to very specific gravitational waves. So I just wonder if you have a free fall atomic clock, can you also do that, or are you limited by this pi pulse that you have to make in the middle?
I think so. I mean, in fact, in some of the slides, I don't know if Guillermo had the slides, but it showed that Jason Hogan and Mark Kasovich, Peter Graham, had the proposal of basically same thing of basically shooting laser back and forth to accumulate the phase in phase with a possible gravitational wave and can build up the signal. I think that was exactly the same idea.
Right. So I know that works for atomic interferometry, and I just wondered if kind of atomic clocks and free fall that also kind of would be the same way. Yeah.
Well, the atomic clock in SEM4 is basically atom formula, right? That's the key point. And when you have free fall, then you have to add a third pulse in the system to take care of the velocity dispersion. And at the same time, because it is in free fall, so when it absorbs photons, then it will have a recoil, and that recoil give you the excess term that is sensitive to the change acceleration of the atoms, and therefore more of an atom formula scheme rather than clock scheme. Yeah. So internally, it's all we're treating the internal oscillation of atomic system as a clock itself. And so it's sort of more of a passive clock. And so it's basically, it's all these approaches that, for the lack of having a very good laser to be able to get to the 10 to the minus 19s, we don't necessarily have to build the actual clock. We just use the ensemble of atoms as a reference, as a clock, and deal with laser noise some other way, which basically is just cancel out the laser noise.
At the 10 to the minus 19 level, when you say that, do you mean 10 to the minus 19 at 1 second of averaging, or because of course we've got these results where they present, but they integrate down for like thousands of seconds.
Right.
So these phenomenal numbers are sort of heroic averaging down, but I've got these time varying signals, so I'd like to track them. So I'm just curious, how should I think about the 10 to the minus 19? At what averaging time is that?
Well, yeah, that's a very good question. So it really depends on the interrogation time, and if we use strontium, then we'll possibly have 100-second interrogation time, and so then you plus whatever the number of atoms you have, the signal noise, you can calculate what the short-term stability might be. But I don't think we'll get to the 10 to the 19th, but I think in like less than an hour, you should be able to get to 10 to the 19th. I mean, others may comment better that more realistic numbers. I think Jun Yi's first talk of the conference showed that how fast eventually you can get to. I think it's in a couple of hours you can get to 10 to the minus 20, 21st.
Yeah, but I think the short-term stabilities are still a work in progress, like the 1 second, if you need the bandwidth. And then as a follow-up, I do want to make the comment that there's a fundamental role to the clock transition in these sensors, but they're really not clocks. Really, the key thing is that they're phase memories.
Yes.
And I like that sort of, you said it's sort of, look, it's a phase memory. So at some point, if you ran a pi over 2, pi over 2 sequence, you're totally fine if you add additional pulse that actually takes the excited state clock and actually maps it onto a ground state. You do not have to accrue optical phase during the entire evolution period. And therefore, I find that a little bit liberating in thinking about these experiments, because you begin to realize you can talk about it as clocks, but you don't have to. It's really a phase memory.
Yes.
And so there are other tricks you can play that might actually sort of relax the requirements on the atoms you're using, or other kinds of pulse sequences you might want to think about. So anyways, I just wanted to.
Yeah,
I saw that sort of
remark.
Yeah,
in the phase memory picture, you don't really care.
Exactly,
you basically you accumulate some phase.
Yeah.
And that phase is common to the other one.
But the point is, it's more like it's a weird, like, delayed homodyne. It's like I take a pulse of light and I record its phase without actually interfering with another laser. I write it down on the atoms.
Yeah, it's written on the atoms, so without actually read out. Yeah.
Exactly. So it kind of replaces that other arm. Right. Anyway, so that was just a comment. I think it's a little bit liberating if you start thinking of it not as clocks, but as a quantum memory.
Two quick questions. Did you look at a multicolor laser system to help disentangle some of the systematic errors? And how's the sensitivity of the new tetrahedral design compare with the older BBO design?
We actually, honestly, we haven't compared that directly. The reason is that it was focused on So it's focused on the basically inverse law violation, square law violation in the solar system. And the difficult challenge over there is that unlike gravitational wave detection, it has certain frequency band you can work with. And in inverse square law, you are more or less looking at the DC measurement. And so that's very challenging. And if you just totally have the average 3 years and have one parameter that can average to, we are looking at the trace, I didn't mention that trace of the gravity tensor, which is supposed to be 0, and it will be very hard endeavor. So what we wanted to, in the context of Galilean field detection, is actually have a sort of elliptic orbit to have some modulation and to get out of the systematics a little bit better. And so now the other comments in terms of gravitational wave detection is sort of, initially was a byproduct, but then it was pretty obvious to us and pointed out to us many times that we know now the Galilean Weinstein screening is it's motivated, but it's already ruled out or possibly ruled out by the gravitational wave detection or LIGO already, and so it's sort of more of serve a benchmark for us to motivate us for doing more probe of violation of Newtonian gravity, and because the science model is not very mature, it wouldn't, NASA or any funding agency wouldn't spend $2 billion to fly this mission. So you need some other science or broad spectrum and science product to support that mission. And so some of the science possibilities are exactly for that. And since mid-band gravitational wave has been discussed quite a bit, and there's tremendous interest, and partly also because of the gap between LIGO and LISA, and so there's gap there. And so this is where the gravitational wave detection fits in. So yeah, we have not really pushing this idea to be the gravitational wave detector.
All right, any other questions? Okay, well then if not, let's thank Nan again and all our speakers.
Thank you for sticking around.